upper extremity amputees to regain their mobility and independence, many adopt the use of a prosthetic device. Typically, this includes a prosthetic liner, which helps to cushion any impacts on the limb, a socket, which acts as a coupling between the limb and the prosthesis, and the prosthesis itself. However, the residual limb is not accustomed to the loads imposed while walking, which can create discomfort for amputees. This discomfort is caused by high stresses and uneven pressure distributions when the load is applied, particularly when these high pressures target more sensitive areas of the amputated limb. Specifically, high compressive loads can cause pressure ulcers in the muscles underneath the amputated bone. However, the most common discomfort amongst amputees is more surface level. High shear and compressive loads at the surface of the limb and the interface between the stump and the liner can cause irritation, breakdown, and blistering. This is where stiffness tailoring comes in. By manipulating the material properties and structure of the prosthetic, it is proven to be possible to control how the load is absorbed. By aiming to have as much of this load as possible absorbed by the prosthetic liner and the socket, the organic tissue of the amputee's stump will experience lower stresses. This, coupled with a more uniform pressure distribution throughout the biological soft tissue, maximises user comfort. Today, I'll be covering how my project partner and I approach stiffness tailoring of prosthetics to maximise user comfort. At the forefront of this project, we knew that we had to investigate exactly how the relevant pressure and stress distributions can be altered by changing the material properties and structure of the prosthetic, as these properties strongly correlate to the user comfort. Once our scope had been defined, we were able to plan the logistics of generating useful results. We began with simplified computational models so that both of the models and results could be easily verified and understood. We then stepped it up to more complex and thus more accurate simulations and models. We began with a two-dimensional cross-section of a simplified assembly with a uniaxial load. This load was taken as the highest component of force experienced at the flat foot stage during the gait cycle, where the maximum loads are experienced. Through iteration and validation by comparison to the literature, we were then able to investigate the effects of more complex multi-axial loading situations, which is much more realistic of a representation of a transtibial prosthetic assembly. By creating a three-dimensional model, these effects could be investigated. Implementing the knowledge we had gained with the previous model, we were able to analyse the effects of varying specific components of the system. We approached this by identifying all the plausible variants in the system. Obviously, in the design process, you can only verify the properties of the liner and the socket. However, we also knew that the limb tissue would vary from patient to patient. We narrowed down this investigation to focusing on the prosthetic components and the adipose layer. Varying the liner thickness shows a near-linear relationship. With increasing thickness comes a reduction in peak stress. Although, in saying this, practical limitations limit the thickness that a liner can be. Issues with compliance and manoeuvrability would rule out liners at the upper end of the tested scale, and additionally, production of thinner liners would prove challenging. In comparison, socket thickness shows a negligible maximum change in thicknesses higher than 10 millimeters. This was expected as the socket is significantly stiffer than the other materials, so large increases in thickness would not affect the stiffness distribution as significantly. This trend was also found when adjusting the socket stiffness, where a softer socket would result in less stress at the interface. However, this too sees practical limitations, particularly with excessive deformation of the socket. When varying the liner stiffness, again, a near-linear relationship is found. That is, with decreasing stiffness comes a decrease in peak stress. It is evident that the liner's effectiveness is limited by its thickness. Then, to investigate how this stress may vary from patient to patient, we investigated a varying array of adipose thicknesses. This had a very similar effect to that found with the liner, which a linear relationship showing that the thicker the adipose, the smaller the peak stress. This was expected, but what surprised us was that the adipose was 5 times more effective at reducing the stress than the liner. This suggests that a more effective liner should incorporate the same hyperelastic behaviour exhibited in the adipose. After these had been completed, it was necessary to validate our results by creating an experimental model. We were able to get material data from each of the simulants that we used, and we inputted these into our computational models. When comparing the results, the discrepancies were marginal, and it was found that boundary conditions that created a plane strain condition, which allowed lateral expansion, most accurately replicated the found results. To answer our research question, we now know that it is beneficial to tailor both the thickness and the stiffness of the prosthetic liner. We found that this reduces the compressive stresses experienced and therefore limits the chances of tissue irritation, breakdown, and blistering. We also recommend that further investigation into hyperelastic materials to mimic the superior cushioning that adipose exhibits. Thank you all for your time and attention today.